Alright, part 2. So the rules that work with the numbering of Kant-Ingold pre-log rules are to do with the rules work by numbering the 4 directly connecting atoms in order of their atomic mass number. From this we give them the priority. So the highest atomic number gets priority 1, second highest atomic number gets priority 2, and etc. etc. So if we're comparing E versus Z, for E, priority 1 and 2 on different sides of the double bond, i.e. the 2 atoms with the highest atomic number are on the same side, as seen here. So, well, these are the same mass, but either way, on this side here, see, the methyl group is going to be more than the hydrogen group here, and same on the other side. So the heaviest groups, N-taken, which means opposite, so on the opposite sides of the double bond. That's most important. I'll mention the double bond here. So that's why this will be an E enantiomer or an E geometric isomer. There's 2 types of geometric isomers. You've got optical isomers and geometric isomers. But so in this case here, so I don't want to say priority 1 and 2 because they're both the same mass number, so I'll use this one here, this bottom one here. So R1 is more than R2. So R1 is heavier than, so R1 is heavier than R2. So then you have priority 1, priority 2, and then you don't really care about these ones here. You probably get the same priority. So the heaviest groups are on either side of the carbon-carbon double bond. So then you call it, this will be an E enantiomer, or E geometric isomer. For Z, priority 1 and 2 are on the same side of the double bond, i.e. the 2 atoms with the highest atomic mass number are on the same side. So for an example here, butene is a Z geometry because the 2 methyl groups are on the same side of the double bond. So you have your 2 heaviest groups here are on the same side of the double bond, and they can't rotate obviously because of this double bond here. So this is your priority 1 and priority 2. Say that for just say that for now because obviously they're the same mass, but priority 1, priority 2, the highest priorities are on the same side. The 2 highest priorities, 1 and 2, on the same side. That's what makes it. That's what makes it a Z enantiomer. So Z just means zusammen, which means together. Just need to remember that, and you'll be fine. That's an example here. You may need to know. So I have fluorine. I've made a better example here. So Kant-Ingold pre-log rules. H is 1, carbon 1, fluorine is 9, chlorine is 6 plus 3, so that's 9 as well. So there's no actual geometric you can't have geometric isomerism on this compound because on this side they both have the same mass. So fluorine and methyl groups have the same mass. Because of that, there's no heavier group on a particular side. Therefore, there's no optical isomerism displayed. There's no geometric isomerism displayed on this compound here. So, yeah. Although it may appear because of it may appear like it does, but it doesn't. So just gotta make sure you count the mass numbers, because this one clearly doesn't have any geometric isomerism. So earlier we talked about, in the part 1 video, we talked about the different types of isomerism. So distinct compounds with different physical properties and sometimes different chemical properties. That's what isomers isomers are, but they have distinct compounds with obviously different physical properties, which give them different chemical and sometimes different chemical properties. But you usually focus on the physical properties. Structural isomerisms have the same molecular formula, but their atoms are bonded together in a different formula. So stereoisomerism is have the same molecular formula, and the atoms are bonded together in the same way and the same order, but they're arranged differently in 3D space. Kind of think about it like this. So isomerism is all of this: structural isomerism, chain isomers, position and functional, and you have this stereoisomerism, which is EZ isomerism, EZ stereoisomerism, EZ stereoisomerism, also known as geometric isomerism, stereoisomer. I can't speak today, but yeah, geometric or EZ, same thing. Don't get confused between the two. And there's optical isomers as well. Not always. These are the ones which are not always superimposable. Non-superimposable. So I was gonna say not always. Non-superimposable images of non-superimposable. So one thing you need to understand about isomerism is that they have physical properties. The chemical properties don't really, unless it's like a functional group isomer, unless it's a functional group isomer, sometimes stereoisomers as well. It doesn't really affect the chemical aspect of your compound, but these do have major effects on your physical aspect of your compound. For example, chain isomers. So ethane has two possible structures. So why did I say ethane? It's clearly butane. Don't know why I said ethane there. So anyway, butane has two possible structural formulas here. You have standard straight chain butane, or you have 2-methyl propane. I'm going to explain. So butane and 2-methyl propane are structural formulas. Structural isomerism. I can't speak today. Butane and 2-methyl propane are structural isomers of C4H10, and they both belong to the same homologous series. They're both alkenes. They're both alkanes, sorry. Therefore, they share similar chemical properties. However, they differ in their physical properties. All right, so my point here is that butane has a boiling point of minus 0.5 degrees Celsius, but methane has a much lower boiling point of minus 11.7 degrees Celsius. So you're thinking to yourself, why is that? So it's important to understand the bonds that form with these compounds. Butane, these form van der Waals forces. There's no oxygen, there's no electronegative groups here, so they form not very strong van der Waals forces. That's hence obviously not very strong, hence a very low boiling point, less than 0. But they form van der Waals forces. In order to actually get the maximum number of van der Waals forces, you want to have something that's straight, not many kinks to the structure. You want to form as much bonds as possible. The more bonds you form, the more energy that's needed to break those bonds. Hence the higher the boiling point. Anything that disrupts a structure means that there's less bonds. And if, as I said before, less bonds means less energy. There's less bonds to break, less energy to break all the bonds. And so that it has a lower boiling point. So butane here is straight. So it means it has a very good lattice structure when it tries to form. If you try to think of another butane molecule here, and you have your hydrogens here. You see how it's a clean van der Waals bond here. Clean bonds are forming. However, if there's 2-methyl propane, this methyl group here at the second carbon kinks the structure. It can't form. It's very difficult to form van der Waals forces. I'm not going to draw, I haven't got space to draw, but if I was to draw this again and try to form the same bond, it's much harder because this group here is in the way, and that prevents this. It's obviously not preventing these from forming, but it prevents some of the van der Waals forces not forming between this carbon here and another of the same compound. So overall, this will have a lower boiling point because it can't form as much van der Waals forces, and hence it's going to have a much lower boiling point. Saying here. Oh, and that explains it as well. So 2-methylpropane gets stacked upon another 2-methylpropane molecule. It forms less intermolecular bonds, so van der Waals forces are intermolecular bonds, than butane, which can form more bonds because it can it can stack much more easily. So it stacks less easily than butane molecules. So butane forms stronger bonds because it can form more, and 2-methylpropane can't form as many bonds. So same. So anything that has same as position isomerism as well. Same functional group in different places. All these branches just reduce the chances of you actually being able to form many van der Waals forces. The three main intermolecular bonds that you need to know about, those are hydrogen bonds. Is this hydrogen bonds, van der Waals forces, and covalent bonds. Ionic bonds as well. Ionic bonds, but it's the understanding is that hydrogen bonds are the strongest bonds that you can form. So hydrogen bonds are number one. Then it's covalent. Probably should have used more space. Then it's ionic. And then at the very bottom will be van der Waals. Van der Waals aren't very strong bonds by themselves, but if you have hundreds or thousands of these bonds forming, or probably millions of these bonds forming compared to maybe a few ionic, because you want some ionic salts, like, you probably have like 5 grams of an ionic salt compared to an entire liquid of butane or whatever it is. So it's probably gonna last longer than some of these compounds here, but the bonds are stronger, but the amount of bonds also affects how its boiling point for a compound as well. Anyway, also you need to know about your UPAC naming. I don't know if you've probably really need to go over it, but UPAC name, you start with the longest chain of a compound. So start from here. You always start with the side that has your branch or your functional group that's closest to the lowest number. For example, if I wanted to name this compound here 1, 2, 3, 4, 5, so 2-methyl 2-methyl pentane, because there's no other group, so just have your two. At carbon 2, there's a methyl group, so 2-methyl pentane, as seen here. This compound here, if I go from either side, it'll be the same. 1, 2, 3. 1, 2, 3. 1, 2, 3. So yeah, you want to go from alphabetical order as well. So got 3-ethyl. You also 3-ethyl 4-methyl hexane. I do think so. I'm not entirely sure if that's correct, but I do believe that's the right naming of it. 3-methyl 4-methyl hexane. So you start off with your longest chain. 1, 2, 3, 4, 5, 6. That's your longest chain, unless 1, 2, 3, 4, 5, 6. No, same longest chain. So, and it will both be at 3 anyway. and then you go along from the side, you're gonna have your chain, your side grouping, and this will be the first group here. So at carbon 3, there's an ethyl group. At carbon 4, there's a methyl group. There's no other one, so you got 3 methyl, so 3 ethyl. Always put your side groups at the beginning, so 3 ethyl, 4 methyl, and then your longest group at the end, hexane. I think that's it really.